And you may be thinking, I would like to have an open source endpoint forensic solution with real-time data, ability to investigate past action, and it's sure. But wait, there is an option, something that is being actively developed, in use for the last 2 years, written by this man, supports multi-platform, so Linux, Windows, and Mac, does memory analysis, does disk analysis, even does some network analysis depending upon the OS, and it looks really cool, but most importantly, look at that logo. That is a freaking alligator with a detective hat on it. Easily makes this the best product of the entire conference. There are no t-shirts or stickers yet. I have asked. I would have taken them if he did. But this is Julian, and he's going to talk all about MIG, and I'm very excited to hear about this.
Thank you. Well, great. Now I have to make t-shirts. Thank you. And stickers. Hi, everyone. My name is Julian Béant. I'm a French guy living in the US, working for Mozilla. And I work about 50% of my time on MIG and developing MIG. So let's start with a quick poll. How many of you work in an organization that has more than 10,000 systems? Okay. 100,000? Quite a few. I know there are people from Google here. Actually, I think he's speaking in the other room. But so we have that kind of problem at Mozilla where we have a lot of systems, a lot of them. And it's just impossible to do investigation on more than, realistically, 200 systems by hand. Even if you do parallel SSH, PSSH, you can probably do 500, maybe 1,000 systems if you're lucky, but it's going to take forever. So this morning, in the panel about finding the needle in the haystack, they talked about the visibility problem. And MIG attempts to solve that visibility problem. We know why we need it. We know what we want to look at. A bunch of people have talked about in-depth analysis of systems, what to look for on a Windows system, on a macOS system. MIG is a project that solves the how you're going to do this. So I'll be honest, I'm not really a forensics guy. My background is really in web infrastructure security, large-scale distributed systems, and how we secure them. So 2 years ago, when I joined Mozilla, my boss at the time asked me, hey, can you write a digital forensic platform? I was like, oh, interesting challenge. How am I going to solve this? And the main problem we had was not necessarily extracting data from the systems, was being able to do this on a large-scale fashion. So I work in the operations security team at Mozilla, and what we do is really, we're called operations security, but we're incident response. And we're also security consultants for everything that happens at Mozilla. We do the incident, we handle incidents, we help developers design and implement security controls, and we build tools. Probably you've heard of, well, MIG is here. There's also another project called by my coworker, Jeff Briner, called MozDef. We do a bunch of work on NSM and a bunch of smaller tools. All of that comes from the OPSEC team at Mozilla. So, Apt 1. I'm pretty sure everyone in this room has read this report at one point or another. And a few years ago, really, we didn't have too many things to look at on an endpoint. We had OSSEC that was looking at a bunch of stuff and alerting us when an alert was triggering. And then Apt 1 came out, and suddenly we had signatures and IOCs to look for. And everybody was like, how am I going to look for them? I have an MD5 or something. I don't have antivirus on my servers. How do I go in and check that I don't have this binary everywhere on my systems? And no one could really solve that problem. So we started looking for ways to solve that. And the most obvious way was, well, we have SSH everywhere. We can just write a small script, run it via SSH, and do that across the entire infrastructure. That works up to a point. That was problem one. It's 2015. Everybody has OpenIOC or some other XML soup, YARA rules, and sometimes just an indicator that something on Twitter, like somebody saying, hey, if you find this file on your file system, start freaking out now. And we need a way to check for it. But at Mozilla, we're also worried about something else. We're worried about that unfortunate comment. And that is actually something that we see a lot more often than IOCs. It is git commit -a followed by git push on GitHub. We're an open source company. A lot of our repositories are public. And very often someone would just run that command and end up with AWS credentials on GitHub. That happens a little too often. This is usually how they feel about it. This is usually when they come talk to us and say, so I put those credentials on GitHub, and we're like, now what? Well, now you need to go check on every single server. First, you need to rotate and cancel, revoke the secret, and then you need to rotate it from all of your systems. And it's hard to do, because we have tons of applications, and one might be using a key from that particular set of credentials, and we don't know where it is or when it was used, and we're going to revoke it, and the application will break, and a bunch of the infrastructure will go red, and everybody will freak out. So this is when we use MIG, and with MIG, we run that kind of command that will look for a file in, for example, /root named Bodo that contains the content ABCDEF 1, 2, 3, 4, 5, 6, a part of the key. And we add some filters to make that faster. We only check for files that are smaller than 1K, and we only go 5 levels down the directory tree. That's what MIG is for. It's for retrieving, it's for finding systems that we care about at any given point, because something happened, and we need to scan our infrastructure, and we need to figure out where we need to do work. So let's step back a bit. We're Mozilla. And that is actually a very interesting point, because I was talking with a bunch of people at the conference, and we have a culture that is probably very, very different from most corporations. We're out to build a better internet. That is what people at Mozilla want to do. We do Firefox, we do a bunch of prototyping, experimentations, we do Firefox OS, and all these things are really research and development that we transform into products. And what that means is that we need to iterate fast, and people want to take risk. And there's a very, very strong startup incubator mindset where we focus on the feature, on the experimentation, and everything that's costly, we may consider it when we transform the thing into a product, but not necessarily. There's minimalistic centralization. Groups are allowed to experiment in their own corner, in their own environment, and everyone at Mozilla knows HTML and can write and host a website. Sometimes they will ask us how to do it, but not too often. So what that means is that we have a lot of diverse groups doing things in many, many diverse ways. And this morning, one of the panelists was saying, I don't understand why we can't just lock down these laptops. It should be easy, right? Yes. Try to do this in a place like Mozilla, and you will have a riot. Laptops belong to the developers. They are creative people. They want to be able to customize it. They want to be able to do whatever they want with it. They want to be able to experiment, and we just can't lock things down. And it's almost true for services. So for us, security at the perimeter just doesn't work. We can't just put an IDS box at the edge of the network and say, hey, we got everything. That doesn't work because we have something like 400 active websites. And some of them are in data centers, some of them are in AWS, some of them are, I don't even know where they are. Not too long ago, I discovered that we had a partnering Mozilla site with a Chinese search engine hosted on a box in the Chinese office, in the Beijing office. I don't even know where this is and how it got there. But it's there, and it's a production site. Totally legit, nothing wrong with it. It's just completely out of the scope of any security practices. We have a dozen offices and hundreds of people who work remote. 2 data centers, something like 30 or 40 AWS accounts. We use Heroku, we use Rackspace, and all of that is disconnected from a central network. Sometimes we will create a VPN tunnel when we need to have 2 pieces talk to each other, but most of the time it's very decentralized. So that's what incident response looks like. And that's how it feels like. When we have to look for something, it's really, really difficult to even find the owner of the service, the people who have the key to get in and actually go look at the system before we can even say, well, something happened to it. So we have this massively decentralized environment and one OPSEC team trying to be able to have access to places so we can do stuff. It's very different from a corporate environment where you can just centralize and say, this is our corporate policy on how we deploy systems, and they must all do this thing. So we shape our operations security team to try to be as efficient as possible in that environment where nothing is really centralized. And this is what I like to call the OPSEC trigram. There are really three things we care about in the team. The first one is expertise. It's having good people, people with skills, domain experts who can just jump in on a problem and really help understand what is happening. People are really important. Intelligence or visibility, the same thing, is knowing things about your environment. If you don't have intelligence, even if people know what to look for, you don't know how big the incident could be. You don't know where to look for possible propagation of the incident. You need intelligence. And reactivity is also an important point. If it takes you 3 days to get people access to the system and start looking, you're done. The hackers are already gone, and there's nothing you can do to save your systems. So you need those three things together. And MIG helps in the intelligence and the reactivity aspects of it. So these three problems. Visibility, we have too many systems. And they're doing too many things in too many ways. We can't reach them. We can't get SSH access to it. We can't get AWS accounts to it, or Heroku accounts to them. And none of them are identical. We have, I believe, 4 or 5 different Puppet repositories managed by different teams. And when a new team, when a new experiment becomes a product, often they bring in their own operations. So eventually we try to consolidate all of that into something that makes more sense. But it's very, very hard to take the entire provisioning infrastructure of a product and merge it into something else. So often we just keep that Puppet repo and whatever log centralization mechanism that was set up with it and make the same people manage it, but it's on Snowflake. So back to the forensics aspects of it. Hardcore forensics will always require having direct access to the system. If you need to look deep inside the memory of a running system, deep on the file system or even the BIOS, you need to have access to it. There is no way around it. You either need to take an image if it's a virtual machine, or you need access to the hardware if it's a server. But 99% of investigations are actually very, very simple, where you don't need that kind of in-depth access. And most of the time, I was just, right before this presentation, I saw a tweet about the hacking team, one of the indicator that tells you to look inside var crash or var TMP for a file called .report. I see someone nodding, you've seen that one, right? So now you're like, okay, fine, well, how do I go check for my Linux systems? I have about 6,000 Linux systems connected on MIG right now. I run a command. I told MIG, hey, go look inside var TMP and var crash and tells me if you find anything called report. And in a minute, it was done. Give me the result. Nope, I don't have it anywhere. That is 99% of our investigations. It's not something we spend 3 days doing. It's something we spend 30 seconds doing. And once in a while, we will find that one indicator that tells us we have something that may have gotten hacked. And this is where we get everybody on deck, DEFCON 1, everybody starts focusing on this thing, drop everything else. We freeze the box, we look at all the possible connections, and we really investigate it. And the faster we run an investigation, the more we will investigate. It happened to, I'm sure, everyone in this room that you see an indicator, and you're like, this looks like it's really complex to look for it. I just can't do it right now. All right, fine, we skip it. And we know we're not covering 100%. We know we're not covering everything, but hopefully the ones we're skipping are not the ones that matter. Well, the thing is, when it's not costly to run an investigation, you really reduce that delta to a minimum. You can investigate a lot more. And we do it for all sorts of things. Someone leaves the company, and we want to make sure that his accounts have been removed from all the servers. Fine, on Linux, it's a line in etc password. You want to check that everywhere? Use MIG. we see, well, hey, there's an OpenSSL vulnerability coming up in 2 days. We want to see which version of OpenSSL is used on which servers. Fine, we use MIG for that. Super easy. We found an IP address. We can call netstat through MIG, and we use it for that. The AWS example I was talking about before. Or sometimes we see something, like a weird host from an experimentation, running a weird software, running something we don't really understand. And a few weeks later, we learn that that software is linked to a possible hack, and we want to find it again. Well, needle in the haystack is a lot easier to find when you have a tool that's distributed everywhere. So 2 years ago, that's circa 2013, we couldn't find a tool we liked, so we built one. I'm going to talk here very quick about GRR. GRR, rapid response, because the G, I've learned, does not stand for Google. But it is a tool built and led by Google. And it is a great platform. It is a fantastic platform. It has capabilities that MIG clearly doesn't have today. The issue, when I was evaluating, at the time we were using OSSEC, and there's just no good way to query OSSEC remotely. And when evaluating GRR, the one issue I had with it was that when you run GRR, it runs an agent on your system, everything's fine, but it doesn't run the investigation on the system. It grabs the data, copies it into a central platform, and then does the analysis on the platform itself. That means, one, you need to transfer the data back to the platform, and two, you need to have a massive database to store all of your artifacts from your entire infrastructure. And Google can do it. They have money we will never have at Mozilla, but we just can't afford it. We don't have that kind of capabilities. And there's also a strong privacy aspect to it. MIG currently does not run on end-user laptops at Mozilla, but we're considering it. And when you run it on end-user laptops, suddenly your investigation team has access to all the files of everybody in the company. And when you're in a corporation, you can enforce that. But Mozilla, we're still hippies. We don't do these things. Privacy is a strong factor to us. So retrieving data from the endpoint was a problem. And that's why we decided to build a platform that does investigation, that has similar capabilities, but does not retrieve data from the endpoints back to a central server. All right, let's do some demos. They are recorded, so they should work. I will let you enjoy this GIF one more time because it's an awesome GIF. I love this one. All right. Would you mind to rewind that video and play it again, please? I think. Could you go back to the beginning of it? That'd be great. Excellent. Thank you. So what's happening here is that we are on an investigator laptop coding the MIG command line and checking for something in etccronD. And what we're looking for is a file that contains the string bad password. And we press enter, and the investigation, because that's really what we call a MIG action, is sent, as we see, to 1,251 agents. Now this recording is real time, so it gives you an idea of how it progresses. It is sent to the MIG platform and processed server side. And I will just take a few seconds to come back. And there you go, it comes back. And you see that out of all of the systems that were investigated, one of them, called obsec1.private.phx1 mozilla.com, has that string in the file called etccronD somejob.inactive. So what happened here is this. And I'm going to talk really about how MIG works at the transport pipeline distributed investigation level. So I'm the investigator on the left. And when I call the MIG command line, I really call a REST API. And I send it a JSON file saying, go look for this thing. And on the server side, the API writes it into the database, a Postgres database. And there's a scheduler that controls sort of the messages being passed around. And the scheduler takes that new action, finds out which agents need to be contacted that are currently online for it, and passes them their own little investigation document. Now, this goes into RabbitMQ. If you're not familiar with it, RabbitMQ is a messaging queue system that does publication subscription. And all of the agents, regardless of where they're located on the planet, are connected to that one RabbitMQ cluster that has a public address. And by being connected to that RabbitMQ cluster, they receive a copy of the investigation message in real time, download it, run it locally, compiles the results, and sends a response back. They all get back into the RabbitMQ cluster. The scheduler grabs them, writes them into his database, and the client, on the other end, retrieves the result and says, okay, I only found one host that has this marker. So let me show you a few more demos. Same thing if you wouldn't mind rewinding it and playing it. So here, thank you. We're looking for, another thing we really like looking for is private keys, because people tend to leave private keys everywhere. So if you want to look for private keys on your folder, same thing, you call the MIG command line. And here we're going to reduce the scope of the investigation to a subset of servers, of agents, that have a tag on them. And they have that tag, operator, that says they're operated by the OPSEC team. And we say, okay, go look into /home on these agents and look for files that have the content begging RSA private key. We also reduce that investigation to 5 level down the directories, and for files that are smaller than 2 kilobytes. And we just pipe, since it's all bash, we just pipe the results to filter them with a hawk a little bit. And the interesting part here is that only 19 agents get investigated. And the targeting aspect is important. When an agent is just this little binary that runs on a server. When it connects to the central platform, it sends a number of metadata about what it's running, what kind of system, what IP addresses, a few tags that are built in, and we can use this information to target only a subset of the systems we have. So you don't always have to investigate 10,000 or 100,000 systems. You can just investigate a few, like the ones that are named MySQL, for example, things like that. And here we see that that one server, external scan 1, had this marker in 3 files, and they're listed at the bottom.
Will it automatically ask that same question once the server comes back online? If you go back a screen at the end there, if that port failed, I assume that's because they were unreachable?
Yes. So in this case, we have an expiration, the -E at the top, that is set to 30 seconds. So it will wait 30 seconds for all agents to process it, and the servers that are offline are not processing it. If you set an expiration to 24 hours, for example, it will wait 24 hours before finishing the investigation. And the servers that come back online, when they reconnect, the MIG agent on the servers will reconnect to the RabbitMQ cluster, and they will have pending actions in there, waiting for them in the queue. Those actions expire automatically after 24 hours. But if they are pending, it will run them and send the results. So that's actually how we do investigations on systems that have spotty connectivity. Or if you would do investigation on end-user laptops that might connect so every day or every 2 days, you would use a long expiration like that. All right, another video here, if you don't mind playing it. So MIG has several modules, and we looked at the file module so far. This is another module that queries netstat information. And same thing, we set an expiration of 20 seconds, and we look for that specific IP. And what it does is, on Linux, for example, it will go look into /procnet TCP and procnet UDP for connected sockets. And if it finds that IP in there, then it will return positive results. On Mac OS, unfortunately, we don't have the APIs to go look for that, so we have to call the command line tools. And actually, that's probably something I should ask to the Mac OS experts around here. And Windows, the same thing. So here we found that IP on 2 hosts. And now that is really, really useful when we're investigating, well, for example, most IOCs have IP information. That's the first thing you find. We got this C2C IP, we got this SSH connection from there. You find IPs everywhere. And you can check them in your IDS, but if you have systems in AWS, they may not be behind an IDS, so you may want to use MIG for that. And the other use of it is really when we're trying to locate possible anomalies. Like, are we trying to find where a rogue employee, for example, is connected? Then we could use MIG to say, well, we see established SSH connections to all of these systems. Or you could use a netstat module to say, well, list me all the servers that are listening on port 443, and we'll return you a list of those servers. So that gives you really a tool where if you don't have a central inventory that knows all the things, and you don't record that information and store it forever, then you can use MIG to query it and retrieve that data in real time. It does not give you historical data. If you care about it, then you probably need another tool to do it. But it gives you real-time visibility on your infrastructure. One last, and this one is the latest addition to MIG that will scan the memory of processes. Now, this is only user-land memory, not kernel memory. And it's not a perfect scanning yet. It will skip some memory regions it cannot read, and it does its best to not disrupt the activity of the system. But you can scan inside running processes for particular string, byte strings or regexes. And you can scan, for example, when we had the heartbeat problem a year ago, and we wanted to rotate all our keys, we wanted to make sure that the keys that needed to be revoked were removed from Nginx. Then you can use a memory scanner to go look inside the memory and say, did you find the string from that key? Yes or no? Okay, it has been rotated. No, it hasn't been rotated. If you find a given, for example, a malware that doesn't necessarily have a file signature, but you get a memory signature for it, you can use MIG to scan for it. So here we just really run a command that looks for Nginx processes, -name Nginx, and look for the string tls.opsec.alizom.org. Alizom is Mozilla reversed, it's our staging site. And that's really just looking for an Nginx server that is running a virtual host for this particular domain, which happens to be a TLS observatory, another project of mine. And it found that one server, observer web1, that has this string in 4 processes. And we get the PIDs, PID 64696, 9899, and 700, because there are 4 Nginx workers on that box. So what we're really trying to build here is digital forensics on steroids. Massively distributed means that it's fast. It's really fast to do investigations. It's simple to deploy and cross-platform. I'll talk about that a little bit more in a minute. Secure, don't trust until you verify. And don't spy on data, respect privacy. So let's talk about these 4 points a little bit. Massively distributed. We don't keep state on the server. We just pass messages around, receive responses. Very small footprint to deploy MIG. It's been, I think the database I checked yesterday has been running for a little more than a year and a half now, and it's using 40 gigabytes of storage. It's a Postgres database. So it's minimal. And that is mostly because we don't retrieve data from endpoints. So we don't have to store a bunch of blob that we never want to look at. Simple to deploy. So I'm a security guy, but I'm also an ops. And I spent a lot of time doing sysadmin work. And I've worked with Chef and Puppet and all of these tools. And when you do ops, there's one thing you hate, is deploying stuff. And deploying stuff usually means that you have to deal with dependencies across 5 different platforms or versions of Linux and macOS and Windows, figure out which library is going to break your entire system, et cetera, et cetera. It is a pain. It is horrible to do. So be nice to your ops and give them security tools that are easy to deploy. And if you can't do the deploy work for them, but they just have really to put that RPM package on their repo and push it, then it will probably never get deployed because they really don't have time to deal with that. And with MIG, that was really something that I cared about. And that's really the main reason why we picked the Go language to build it. Because Go, when you compile a Go binary, it's a static binary. Everything is built into it. You take the binary, you throw it on any Linux 64-bit machine you want, it will run. So it's great for us. We just create a basic RPM envelope or deb envelope. We just put it up there, and it runs. You can cross-compile. I cross-compiled the binary for macOS from Linux. Just put it in a small DMG file, put it in our Puppet, and it deploys and it runs. So it's really simple to deploy. Another thing we tried with mixed results was to build the configuration inside the binary. So instead of asking ops to provision secrets on the machine and configuration files on the machine, and if you've worked with Puppet, provisioning an SSL key on a machine is not an easy problem to solve. Then instead of doing that, we put everything into the binary at compilation. So we have build scripts that are specific to different parts of the infrastructure, and they each pull in their configuration, compile it into the static binary, and we just have to deploy that one thing, no configuration file. That does mean the binary must remain secret, moderately secret. Even if it leaks, there's not much a hacker could do with the SSL key that's in there. But it does simplify the deployment a lot. And particularly what is great is that you can just, if you find a system one day that is completely out of scope, you don't want to lose track of it, you take that one MIG binary, you put it there, it takes you 2 seconds, and it runs, and you don't have to worry about it, and it will keep connecting back home, telling you, hey, by the way, I'm this one guy you found 6 months ago that everybody forgot about and might be an entry point to your network. So it's very easy to deploy. It is a pain to build, but it's easy to deploy. Security, so I haven't talked about that yet. Everybody loves to hate on PGP. I love PGP. And we use it a lot at Mozilla. It really is a core component to everything we do in the security teams and in the ops teams. So it just made sense to build the security of MIG around PGP. And when the client, the MIG client, runs that one MIG command to send an investigation, what happens in the background is that there's a JSON file generated that says in there, like we see here, searches S1 pass etc content bad password. And it has a validity period, so it cannot be replayed for too long, and a target, etc. That one JSON file is signed with your PGP private key on your local machine. That signature is put inside the JSON file. You see it in PGP signature. And each agent on the servers, the 10,000 or 100,000 of them, will verify that signature. So the agents actually know the list of investigators that are allowed to run commands. They actually know their PGP public keys. And when the commands arrive, they verify the signatures. So even if someone breaks in, even if someone takes over the entire MIG platform, they can't send anything to the agents unless they have stolen one private key from an investigator. Now, hopefully, the ops people and the security people know how to protect the PGP private key. Otherwise, you have bigger problems. So it's a pretty good security model. You can take over. That was another problem when I was looking at GRR that I had, is that you really trust the infrastructure. If the infrastructure is taken over, well, you have root access to all of your systems. So it is a problem. It's not so much a problem when you can really constrain your infrastructure to specific network accesses, but when, like us, you need to have a significant part of it on the public internet in order for everybody to connect to you, it is a concern. And finally, I'm a big burn notice fan. I used to be a spy. I used to be that guy who loves to record everything that happens in the infrastructure so that I can find that one needle that everybody's looking for. And in doing so, I just burned $300,000 on Elasticsearch clusters, and I don't know how much on IDS, and I recorded everything, and I found that one thing. And it is still something we must do, but there are places where it just doesn't work. We just can't do it. So we tried something different. Let's try to do it without full access to the data. And it is hard. I was yesterday talking with one of my coworkers about how to do vulnerability management using MIG. And the question was, how do we take the package versions we have on the systems and actually compare that with a database of vulnerable packages without retrieving any package version out of the systems themselves? And the technical aspect of it got really complicated. Finally, we found a way to run it, but My point is, if you're not going to retrieve data out of your systems, you need to find creative ways of running investigations. It's more complicated, but it's worth it. So the main concept here is that agents do the work and return answers without returning the raw data. They may return some metadata, limited, but not the raw data. All right, I'll pass very quick on the internals. It's a REST API that receives signed JSON messages, distributes it to agent RabbitMQ, and stores it in a Postgres database. This is what it looks like in the bigger picture. It's a kind of unflattened version of the previous diagram. So on the agent side, you're going to tell your ops that you're deploying a piece of software on the servers. And rightfully so, they're going to be like, okay, how is it running? Well, it's okay, it just runs as root. All right. Oh, yes, and it needs to connect on the network on the public internet. Okay. Are you sure about this thing? Yep. And you want to run it everywhere? Sure. On the main load balancers, the signing servers, everything. Okay, so point is, they care about this thing. So we try to, in the architecture of the agent, to kind of mitigate these concerns by putting the core functionalities, the part that really do the work, go look at the files, go look at the memory, into modules. And modules are segregated. They are running as separate processes. You can kill them if you need to. We will sandbox them at some point to give them just the accesses they need, because there's no reason a file module would have access to the network, et cetera, or would use 100% CPU as a thing. And that's this ugly diagram. I also happen to like ASCII art, I'm sorry. Kind of describes the workflow of actions inside the agent. But the main point is, you can write your own modules to do specific things. For example, if you want to have a module that goes look for a specific, I don't know, that all of your laptop on macOS have disk encryption enabled. That's a very specific thing that is not supported with a module, or you want a special way to do it. You write your own little piece of Go code, and you compile it into the agent, and you ship it. And that module will just be able to do that one thing. So there's really very, very little attack surface to transform that into a remote code execution platform. All right, I talked about the security model already, so I will skip on that a little bit. The important part here is that we can give fine-grained ACLs to various parts of various groups inside Mozilla. So for example, the incident response team would have access to everything, and the sysadmin team just cares about having access to files, so we just give them an ACL that can call the file module, really, and not the memory module, and not the other fancy modules we have. And the way that works is that we just create a list, like here in this document, where we list their public key fingerprints. And MIG will know that only these keys are allowed to call that module. We also have a mechanism to enforce double signature, where we will say, for example, that to call the memory module, you need to have 2 signatures. You need to have a signature or you need to have a weight of 4, and each investigator carries its own weight of 2, so you need 2 signatures, 2 plus 2. And you can do fancy things like that. You could do things like a module that would, for example, freeze a system, lock down all accesses, and say, well, we want to have 2 signatures, and really, the people in the security team only have a minimum weight, and we need to have someone from the legal team to double sign the action before it goes live. You could do things like that. So you know that you're not giving all accesses to just that one incident response team, if that's something you care about. That's what I just talked about. Oh, and one cool feature, since I really like PGP, is that the REST API of MIG is actually not using classic authentication. It uses a PGP token. So when you call the MIG API from your command line tools, and you're actually really just doing HTTP with the API, what happens is that for every request, your private key is signing a token. That token is passed to the API, and the API verifies it and say, oh, sure, you're Julian, welcome. And by just that token, we know the identity of the investigator, and we have a signature of what is being passed. And we don't require an extra username and password to access the API. That's database protection things. These things we don't really care about. One word on RabbitMQ, it's a pain to secure. If you have some RabbitMQ systems in your environment, really recommend you look at them because most likely they are not secure at all. I spent a significant amount of time learning and using the RabbitMQ ACL model, and it is not easy. It's still very confusing. So if you're not sure what to look for in your infra and you see some RabbitMQ server, really recommend you go look at them. Point is here that we use the MQP over TLS, and we use tightly controlled RabbitMQ ACLs between the agents and the public cluster. So there's really very little attack surface for an attacker to connect to the public cluster and take control of your systems. All right, so there are many indicators of compromise formats. You have Yara, you have OpenIOC, everybody's trying to standardize their own. GR has artifact format, MIG uses a JSON format. I'm not trying to reinvent a new indicator of compromise format. What the MIG format is a messaging format, a transport format. But it does happen to be fairly simple. So this is a JSON file that describes things we saw during the shell shock mess last year when shell shock was being exploited and we could find IOCs on tons of blogs and websites and everything. And I collected them into that one action that we run many times throughout the day to make sure that our servers were not being exploited. And I still run it once in a while, kind of like an antivirus signature to see if anyone is using it, exploiting it. So what it does here is that you have a name, okay, you have a target, and you can see here that the target will run this on systems that are either Linux or Darwin and are running in daemon mode. We have some system that daemon mode means the agent is running in the background as a background process. We have some cron mode where the agent just wakes up regularly to check in. And here in the operations, we're coding the file module on all of these paths. And we're looking for various things. SHA-256 signatures, for example. So we calculate the SHA sum of all the binaries in those paths and all the files in those paths, not just the binaries. And we compare it to this SHA-256 signature. And further down, we have some regex signatures for things, files that might contain the busybox string with the echo. There are some others that are below. We have IP addresses, we have things like that. So it's a fairly consumable model compared to when I was evaluating various solutions. I was looking a lot at the OpenIOC format. And in my team, Jeff Briner wrote PyIOC a couple of years ago and spent a lot of time studying the OpenIOC format and how to parse it and everything. And we fairly quickly got to the conclusion that we were not going to reuse it. That we're going to come up with something that you can't just read. It doesn't matter if you have tons of IOC formats out there if all of them are super simple to understand. And that's kind of what we're going for. And I was having discussion with some of the GR folks, and they're kind of in the same mindset. They're not trying to impose a standard. Because what really matters at the end of the day is that one signature you just found, that one byte string, that one checksum, that one IP address, and how you represent it does not matter. If it's an XML file, a JSON file, a Yara file, a YAML file, whatever, if it's just a shell, it doesn't matter. So we need to have formats that do not impose their own syntax on you, that you can just use when you need it very quickly and pass it into your infrastructure. All right, icing on the cake. You can geolocate results in MIG. That's a fancy, not super useful feature. Sometimes it is, but I like maps. And one day I was like, I want to use a GeoIP database. So you can, if you run an investigation, you can say, show me the results on a map. And for all of the positive results you find, it will geolocate their public IP. So you know the public IP because the agent connects to the cluster. And it will geolocate the public IP and tell you, well, that one agent is in California, the other one is in Virginia, this one is in Germany, et cetera, et cetera. That's useful if you have a lot of mobile users. The end goal for this, for us really at Mozilla, is that we have so many people that are remote that the day we run MIG on end-user laptops, we will need a way to geolocate it. So we have a generic security platform. We can do a number of things. We can do investigations. I've talked about that. But we also do a lot of other things. And we actually started consolidating a lot of our security arsenal into MIG. Security compliance, verifying that your systems are following a set of standard controls, is something we do with MIG. I'll talk about it in a second. Vulnerability scanning. We use Nexpose, and it's a great platform, but it requires to have some sort of connectivity where oftentimes we don't. And instead, we're trying to look at MIG and how to do vulnerability management using MIG and the overall standard. If you're not familiar with the overall standard, it's an XML format that defines vulnerabilities on packages. So you can ship the XML definition to your MIG agents, tell them, if you have Nginx lower than this version, you're vulnerable, return something that tells me we need to be patched. And we run that through MIG dynamically. And the great thing is that when that, for example, OpenSSL vulnerability today will come out, we can just make an overall definition of it, broadcast it to all of our agents, and it will come back telling us, well, these 50 servers need to be patched right now. This is called auditing with ODD. Guillaume Descender in my team is our local ODD expert, and he wrote a bunch of ODD Cisco auditing for Linux plugins, including one that grabs ODD events, transforms them into JSON, and feeds them into MozDef. And we can use that to really keep track of what's happening on the servers. But ODD JSON is a separate binary that needs to be deployed in its own special way. So the idea was, well, we already have MIG deployed everywhere. Why don't we make a MIG module that will grab the ODD data and pass it into MozDef? Log inspection is another big project that I think we'll work on. I have hopefully a team of students that will be focusing on that later this year. Kind of OSX style, reading your logs and looking for markers in there, looking for regexes, looking for things like that in a distributed way, because we have a lot of systems that don't feed their log to a central syslog pipeline. And maybe some NSM stuff, maybe doing a distributed TCP DOM system that each system could look for their own DNS queries, for example. So going back to the security compliance stuff, it's really just a way to use the file module like I described above before. And here what we do is that the compliance item is what we call test-driven security. And what we do here is that we look inside etc sshd underscore config for the regex log level verbose, because we want all of our servers to have that parameter set in their configuration. We do another one with check that password usage is off, that will look for example, disabled password login and forced login with keys. That returns in another JSON format that we feed into MozDef, and then we can do graph like this that we can show our sysadmins team and tell them, hey, there's a set of controls that are low level. You're pretty good at it. You're like 88% compliant. That's great. The medium one, the more complicated ones, not so good, 56%. And the high one, like, do you have SE Linux enabled? Not so good, 27% only. Now, not all systems needs to have SE Linux enabled, but there are systems where we may want to have it enabled. And keeping track of that and making sure the systems stay configured the right way is difficult. So we use MIG to distribute those checks, bring back the data, and graph it. So, TLDR. MIG is a platform made of distributed agent, securely queried from a central platform, and to investigate a large pool of systems remotely. And that's it. If you have any questions, I'm happy to take them now, or I will be around the room afterward. Thank you. Okay. So all of my examples are on Linux, because that's really our primary target. We do support macOS. I think the only thing that's not supported right now is the MAC address lookup in the netstat module on macOS, but everything else works perfectly, and we use it in production. Because yes, we have macOS servers in production. And Windows is supported. It does run. I need to polish it up a bit, so it's not running perfectly right now, mostly because we're not really a Windows shop, so it's hard to dedicate time to it. But theoretically, I would say the amount of effort to make it run on Windows is probably a couple of days. Yes?
What's your process for updating an agent? Do you have any modules?
So initially, we were shipping with an upgrade module that would just download a new version of the binary of the agent, install it locally with a verified signature and everything, and run it. But it turned out that it wasn't really necessary because most of our systems are in Puppet, and the ones that are not in Puppet, we can still reach them. As long as we know where they are, we still manage to connect to them. So for now, we mostly use Puppet, and we deploy new RPMs, new DEBs, new DMGs via Puppet when we want to upgrade. Takes probably to reach all the systems a day or two to upgrade everything. Yes?
Do you have a forum page that tells you the agents?
Yes. So two things really. There is a status dashboard in the form of a MIG console. It's a command line console. One back. I don't think I have a screenshot of it. Nope. I'm just going to leave it on this slide because it's the best one. And we do have a MIG console. Now what we're looking for is, instead of having really a dashboard, this is really disturbing, I'm sorry. Instead of having a dashboard that you need to look at, what we're trying to do is to write workers that receive events when new agents connect, so agents disconnect, and trigger an alert when it's not something, or it's something we care about, or an agent is disappearing and we don't see a valid reason for it, and pass it into our SIEM pipeline where we can escalate it. So trying to write, really instead of doing monitoring by hand, we're trying to automate it through Go workers that run in the platform. Any other question? Excuse me? Not through MIG. So we do it with, classic methods, network security monitoring, IDS, things like that. Right. Once we know where they are, we know what to do, we can deploy the agent on them. We're actually trying to run MIG on our switches at the moment as well. And I think we could do some interesting things.